Hello, this is an extra video to explain solutions of an extra question set on interference and resolution practice. We are told that the parallel slits have negligible width. That means we assume they are point sources. We're given that the intensity due to one slit is 22 watts per meter squared due to one source at point M. M is the midpoint of the screen. So it must be a constructive interference point. It's equally distant from both slits because it is the point right across their midpoint. So amplitudes add up and they are equal due to the equal distance, which means amplitude at M will be twice of the amplitude of 1. And we know that intensity is proportional to the square of the amplitude. So if 1A gives 22 watts per meter squared, 2A will give 4 times that, which would be 88 watts per meter squared. Part B is simply a calculation. P is given as the first maximum after M, so the distance MP is S in our two-source interference formula. I want to draw your attention to a very common case. Sometimes questions give you the distance from a maximum to a minimum. That means from a bright to a dark fringe. For sound, this could be the distance from a loud point to a quiet point. That is half the S in this formula. In this formula, we used S to be the separation of two consecutive maxima. Be very careful. Sometimes questions may give you the distance from one bright fringe to the center of the third bright fringe. Then you have to divide that by 3 to get S. So be very careful about using the given distances in a question and substituting that for S. Be very careful that the S value you use in the formula is the separation of two consecutive bright fringes, the center of one bright to the next bright, or the center of one dark to the next dark. Well, we're given that directly. Substitution gives 560 nanometers. In part C, we're told that the width of each slit is now increased to 0.03 millimeters. That means now that we know their width, we cannot assume that they are point sources. And that means diffraction effects cannot be ignored. We have to see that the intensity pattern will be as such that stays within a diffraction envelope. So instead of being like this when they were at like point sources, it will be like this. And explanation of the diffraction effects not being ignored due to the width of the slits being finite, you should say that the intensity at P will be less than before. In the second part of this part C, we are asked to show that due to single slit diffraction, the intensity at a point 28 millimeters from M will be a 0. So we're looking for a point, the first minimum, where intensity is 0. The first point after M where intensity is 0 is going to be the first minimum of the single slit diffraction pattern. So we use the single slit diffraction equation. We have wavelength from the previous question, and we're given the width of each slit. So that would be the angle we calculate. And to find the distance of the first minimum to the center, we need to remember that this must be the same angle as in y over d, where y is the distance from the center of the first minimum using the small angle approach. Substitution into the ratio. I have the diagram here to remind you of what we saw in the single slit diffraction lesson. This angle was the same angle as the angle calculated with lambda over b. This is the width of the half of the central bright. So y over d from the tangent. Remember that we use the small angle approximation to say that this angle over here should be equal to the diffraction angle to the first minimum, the ratio of lambda over b. So calculating that value and substituting the given values for checking this distance, we see that the ratio actually checks out. So we conclude that the distance to that point is going to be that value. You might as well just substitute and solve for y in this problem, which would also be fine. Light from a point source is incident on the pupil of an eye of an observer. The diameter is given as 2.8 millimeters. First, we're given an axis and asked to draw the variation with diffraction angle. This is the single slit interference pattern, but things to watch for. Make sure it's symmetric on both sides. Make sure that it hits 0 here and here. And make sure that that is very small compared to the brightness of the central maximum. And the second part says estimate in radians the smallest angular separation for light of 256 nanometers to be resolved by the eye of this observer. Resolution formula 1.22 lambda over b. Lambda and b gives us the angle. Thank you.